Today we're looking at ways to simplify radical expressions. And our main goal here is to do three things. There's three things on our checklist. Number one is we can't have any perfect square factors underneath the radical sign. We can't have any fractions underneath the radical. And we can't have any radicals in the denominator of a fraction. We're only going to look at that first issue today. And additionally, we're going to look at radicals of higher index, cube roots and so forth, and how to tackle those as well. So the first thing we want to think about is, if I have a square root, for instance 72y to the fifth, and I'm trying to simplify that down, I want to try to approach this in a sense that I'm going to sort these into two different types of factors. The first type is a perfect square factor, because that I can simplify. The other is a non-perfect square factor, and that's going to remain underneath the radical. So if I look at the square root of 72y to the fifth, I'm going to first think to myself, okay, does 72 have any perfect square factors? And I would test it to see if it divides by 4, and it does. And I would test to see if it divides by 9, and it does. I would test to see if it divides by 16 and 25, and then 36. And it turns out that 72 is 36 times 2. So I'm going to go ahead and write my 36, my perfect square factor, in one radical, and then my non-perfect square factor in another. The next thing I'm looking at is the y to the fifth. Recall that y to the fifth represents y used as a factor 5 times. If I split this up, I can take y squared and another y squared with a y left over. So y to the fifth is really y squared times y. So y squared is a perfect, y to the fourth actually, is a perfect square factor. And I have one y left over. This works every time when you take a look at the exponent you have in an expression. If this is an odd exponent, subtract 1. That even exponent will be a perfect square, and then you'll have one copy left over. So in this case, y to the fourth times y. So now all my perfect square factors are collected together. I can simplify those. 6 is the square root of 36. Y squared is the square root of y to the fourth. And then I have this radical 2y left over, which I'm just going to leave in that way. So let's look at some examples. Square root of 16, x to the third. Well, 16 is a perfect square. X to the third is x squared times x. So when I take my square root of my perfect square radical, 4x times the square root of x. How about one like this, the square root of y to the fourth? Well, it's a perfect square standing alone. It's the only factor that's there. I can just take the square root of it, it's y squared. 8x to the seventh. 8 can be broken down into 4 times 2. X to the seventh, that's an odd number, so I take 1 off, subtract 1, 4x to the sixth, and then I have a 2x left over. So square root of 4 is 2, square root of x to the sixth, x to the third, and then I have 2x remaining. Similarly, when there's more than one variable, same rule applies. 12 is 4 times 3. My x to the third, I can split into x squared and x. Y to the 8, that's an even number, so that's a perfect square as it stands. So 2, the square root of x squared is x, and then y to the fourth, and then my remaining radical is 3x. So 2x, y to the fourth, times square root of 3x. Now we've got a situation where I've got a cube root that we need to consider. Well, what do we do with that? Now I'm looking for perfect cubes. So 27 is 3 times 3 times 3. 27 is already a perfect square, as is x to the third. I don't even need to break this down into two radicals. It's perfect as it stands. 27, cube root of 27 is 3. Cube root of x to the third is x. The cube root of 27x to the third is 3x. Let's try another. 16. Now I'm trying to break this into a perfect cube. My smallest perfect cube is 8. 2 times 2 times 2. Okay, good. That goes in my perfect cube radical. X to the fourth. I'm looking for groups of x to the third. I have 1. and then there's an x left over. Y squared, now I need 3 copies of that for it to be a perfect cube, so it's going to go in my non-perfect cube radical. So I take the cube root of this first expression, 2x. My remaining expression stays under a cube root radical, 2x y squared. 32. So 8 is a factor of 32. If I think about my next cube root, 3 times 3 is 27. That won't work. So I have 8 times 4. X to the 7th. So I'm looking for groups of 3. X to the 6th, with 1 copy of x left over. And y to the 9th. Remember, that's y to the 3rd times y to the 3rd times y to the 3rd. It's already a perfect cube. Let's take our cube roots now. 2 x squared, y to the 3rd, and then the cube root of 4x. Let's go here now. 81, already a perfect cube. Thinking perfect squares. It's 27 times 3. C, standing alone, goes in my non-perfect radical. And then d to the 3rd times d squared. So the cube root here is 3d, and then my remaining cube root, 3c d squared. We remember from our product property that if I have an expression underneath the radical sign, a radicand, I can split that radicand into 2 factors, and each gets its own individual radical sign. I can work the opposite direction too. When I multiply 2 radicals together, I can multiply the 2 radicands and write it as one radical sign with the product of those radicands. So 12 times 3 is 36. The square root of 36 is 6. Let's take a look at another example. 3 times 24, that's 72. X times x, x squared. Okay, now let's approach this the same way we did in the last section. I need to split 72 into a perfect square, 36, and an imperfect square, 2. X squared is a perfect square. So now I have 6x times the square root of 2. What about a case like this where I've already got factors outside the radical sign? Those stay outside the radical. 2 times 3. Now I can multiply my radicands. 8 times 18. So that's 80 plus 64, 144 y squared. Now, 2 times 3, that's 6. If I take my square root here, 12y. So 6 times 12 is 72y. One more. Negative 5 times 4 stays outside the radical. Inside the radical, 10 times 2 is 20. X cubed times x is x to the 4th. And then I have a y. So negative 20 outside the radical. My 20 can split into 4 and 5. X to the 4th. And y, standing alone as a factor, goes in my imperfect radical. So negative 20 times 2 x squared times square root 5y. So let's simplify one more step. Negative 40 x squared square root 5y. Moving kind of quick through these, but once you get the hang of it, they do tend to go pretty quickly. Let's think about, can we add and subtract radicals? I want you to think back about when we learned how to combine like terms. And one of the issues we had was we could combine 2 algebra terms if they had the same variable and the same exponent. Similar restrictions apply when we're adding or subtracting radicals. We can only add or subtract radicals when they have the same index and the same expression under the radical. Sometimes, in order to get the same expression under the radical, we need to simplify. In fact, we should always be simplifying radicals before we start to add or subtract. And once we do that, the numbers out in front of the radicals, those are a little bit like our coefficients that we added or subtracted when we added like terms. So let's look at an example. 4 square root of x times 6 square root of x. So these are both square roots. They both have the radical of the radicand of x. So I can go 4 plus 6 times square root of x. This is 10 times the square root of x. Here, I'm talking cube roots, and I have the same expression under the radical. So same index, same radicand. These I can go ahead and subtract. 2 minus 11 times the cube root of 3y, so that's negative 9 cube root 3y. How about this one? I have a square root and a cube root. Very first thing we thought about in this set of notes was we can only add or subtract when they have the same index. These we can't combine in any possible way because square root and cube root, I can't add or subtract those. Here's another example. Cube root, square root, and different expressions under the radical, x and y. This one, I have to just leave the way it is. Let's move on to another type of problem. 50 and 18, my radicals are different, but I have to check and see if I can simplify these first. So 2 times the square root of 50, that's square root 25 times square root 2. 18, I can split into square root of 9 and square root of 2. So now let's simplify. Square root of 25 is 5. The square root of 9 is 3. So outside the radical, I can multiply. 2 times 5 is 10 times the square root of 2. 3 times 3 is 9 times the square root of 2. So I have 10 minus 9 times the square root of 2. So 1 times the square root of 2 will be my solution. One last check. So 2x to the third plus 4x times the root of 8x. Let's simplify here. X squared is a perfect square times 2x. And then I have 4x plus 8 can be split into 4 times 2, so 2x. So I can see that I'm going to have an identical radical here. Square root 2x, square root 2x. So let's simplify. X times square root 2x, not x squared, just x, plus 4x times 2 times square root 2x. So x plus 8x times the square root of 2x. And that's as far as we can go with that.